So in the last video, I defined two operations on congruence classes. So on Zn, if we take a congruence class and we add it to another congruence class, what we mean by that is add those numbers, add those representatives, and then take the congruence class. And if we multiply two congruence classes, we follow the same structure. We multiply the representatives, take the congruence class, and we showed last time that this was well defined. So now what I want to do is I want to write out some tables of multiplication so that you can see how to do arithmetic in Zn. So let's first start off with an addition table. So I'm going to work in n equals 6. So in n equals 6, Zn is going to be represented by just 0, 1, and then all the way up to the congruence class of 5. So if you'll permit me, I'm going to leave off the square braces. When I do my arithmetic here, when I write out this table. Okay, so for each argument and argument, I'm going to add those things together and tell you what you get out in Zn. So the rule is pretty simple. The rule says just add those integers. And so for the most part, I can just write down the sum of the number and the sum of the number. 0 plus 1 is 1, 0 plus 2 is 2, and so on. If I add 1 to 1, I get 2, 1 to 2, I get 3, 4, 5. Here's where I'm going to change. 1 plus 5 is 6. In mod 6, 6 is congruent to 0. So I'm going to go back to those representatives that we get through applying the division algorithm. So I'm going to look for those representatives in 0 through 5. So you can really see how to read which element it goes back to. So 6, 1 plus 5 is 6. That's 0. Let's keep going. Addition, you'll see that it's commutative. It works both ways, right? So a times a plus b is b plus a. So this is going to be 1 plus 2 is 3, 1 plus 3 is 4, 5, and when I get to 6, that's congruent to 0. 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6, that's congruent to 0, and 2 plus 5, 7, that's congruent to 1. Subtract off 6. Three plus 3 is the next thing, so that's 6, that's 0, and as I go down I keep adding 1, so you can see the pattern pretty easy. And as I go down I keep adding 1, right? 4 plus 4 is 8, minus 6 is 2, and so you can fill the last of this in. 5 plus 5 is 10, minus 6 is 4. Okay, so there's our addition table. Every time just reducing it using long division and looking at the remainder. So for multiplication, I'm just going to use a dot for that. 0, 1, 2, 3, 4, 5 again. So 0 times anything is 0, and the congruence class of 0 is just the congruence class of 0. 1 times any number is just itself. And you'll notice that all these numbers are already within the range 0 to n minus 1, so they just remain themselves. Two times 2 is 4, and 4 is congruent to 4. 2 times 3 is 6. I get 0 now, reducing that just by subtracting 6. 2 times 4 is 8, so 8 minus 6 is 2. 2 times 5 is 10. Again, subtract a 6 and I'll get down to something in the range I like, 4. I can write this row again this way, so it's 0, 2, 4. Again, a times b is b times a, and so when you pass to congruence classes, it inherits that property. So where are we at? We're at 3 times 3. 3 times 3 is 9. 9 is congruent to 3 mod 6. 3 times 4 is 12. So I could take 12, subtract 6 twice and get 0. Another way I could see this is that when I'm taking 3 times something, and then 3 times 4, and then 3 times 5, I'm really adding 3. So I'm going 0, 3, add another 3, I get to 6, add another, which is 0, and add another 3, I get to 3. Same thing here, I'm adding 4 each time. 2 plus 4 is 0, 0 plus 4 is 4, 4 plus 4 is what? 8, subtract 6, it's 2. And in this final column, I'm adding 5 each time. 4 plus 5 is 9, 9 is congruent to 3. 3 plus another 5 as I move down is giving me 8, that's congruent to 2. And finally 5 times 5, we could just jump to it, it's 25. 25 minus 24, 24 is a multiple of 6, gives me 1. And you can see this multiplication table for Z6. There's some interesting things that go on here that you've never seen before. For instance, 2 times 3 is 6, which is congruent to 0. So 2 times 3 is 0. So you haven't seen this before in the sense that you've never seen two numbers multiply to give you 0, where both of those numbers were not 0 in the first place. This has big implications for if you're trying to solve an equation. If I have something like, 3 times x is equal to 0, then I don't know that x has to be equal to 0. It's possible that x could be 2. So this throws a big wrench into the works of all of your solving of equations. Another thing which you can see inside this multiplication table is you can see multiplicative inverses. So where do I see a multiplicative inverse? There's actually only one of them creeping about here other than 1. So first off, 1 divided by 1 is 1, or 1 times 1 is 1. Any way you want to shuffle it works. Also down here, if I look, I see 5 times 5 is 1. What that's really telling me is that the multiplicative inverse, the reciprocal basically, of 5 is itself. So it can multiply by itself to give 1. So there are two different solutions to the equation x squared equals 1. There's 1 and there's 5. Notice 5 is congruent to minus 1, mod 6. So you can really think of 5 as minus 1, and then this becomes a little less strange. Minus 1 times minus 1 is going to give you 1. Okay, so now I want to describe properties that addition and multiplication satisfy. And they come in a big group of things. And what's interesting is this group of properties that they satisfy has a name in and of itself. Or rather, we give names to things which satisfy this grab bag of properties. So I'm going to give you a whole list of properties, and then I'm going to tell you that Zn satisfies them. Here's the definition. A ring is the name that we give to an algebraic structure. So a ring is really a triple, R plus times of a set R and two binary operations binary operators, that is, maps from R cross R. They take two things in this set and they produce another thing back in this set. And they have to satisfy the following properties. So here's the list. First off, we have associativity. Associativity of addition. So what is that telling us? That tells us that A plus B plus C should be equal to A plus B plus C. And this is going to be for all A, B, C inside this set, which we call a ring. So it's a pretty natural property for addition to have. What else do we want? We want addition to have an additive identity. That is, there exists an element called 0 inside of our set such that 0 plus A is equal to A, and it's also equal to, I'm going to throw an extra condition, A plus 0. And this is for all A inside our set. And so clearly Zn has that. It's the congruence class of 0. Our next property is additive inverse. You should read this as negatives. So for all elements of our set, there exists another element, B, in our set, such that A plus B is equal to that additive identity which we saw earlier. And so what I'm saying here is really that A and B are negatives of each other. So for every element there exists a negative, something which you can add to it to get back to 0. Oh, and that was 3. Our fourth property is commutativity. Of addition. So A plus B is B plus A for all A and B inside our set. You'll notice that if we have commutativity, we don't really need both of these two laws for our additive identity. We only need one of those. But we'll come back to these 4 conditions when we come back to talk about groups, because this is really the defining properties of a group. Just have a single operation satisfying associativity, additive identity, and additive inverse, but not always commutativity. So these are all nice additive properties. Let's talk about the multiplicative properties that we have. First off, there's associativity, again. That tells us that A times B times C is equal to A times B times C. That's for all A, B, C inside our ring. So, property 6, we have multiplicative inverse, multiplicative identity. So there exists some element, we're going to call it 1 inside of our ring, such that 1 times A is equal to A is equal to A times 1 for all other elements A and R. So if you're familiar with the element 1, it has the property that 1 times something is just that something. And this is going to be our congruence class of 1 in Zn. Next property is, and the last property is the distributive property. Really, this comes in 2 sides, so A times B plus C is equal to a times b plus, be careful, a times c, and the other way around. If we multiply on the right, we get b times a plus c times a. Be careful about the order in which you write these. So this is the whole list of properties for a ring. The one additional property which I'd like to add, which is not in most rings, is this. A ring is called commutative. If a times b is equal to b times a for all a and b inside your ring, which simplifies some of these other laws. So most of the rings that you know are commutative. You know of polynomial rings and all of your, so let's say, real numbers, rational numbers, the integers themselves. One thing which you know of, one ring that you know about, which is not commutative, is a ring of matrices. So you can add matrices, you can multiply matrices, but not all matrices commute with each other. And another thing which is not listed here is multiplicative identity. Right? So you don't always have a multiplicative inverse, something where given an element, you can find another element that multiplies to give you one. They don't always exist. They don't exist for matrices, and they don't always exist for elements in Zn, for congruence classes in Zn. If you went back and saw that multiplication table, you'd realize that nothing multiplies against 2 to give you something congruent to 1 in mod 6. So, I'll end with a proposition. Zn is a commutative ring. For all n. The proof is really that Zn inherits all these properties. From the commutative ring. Z. Now it might sound like I'm cheating and trying to save myself time, but let's do an example and you'll see just how easy this stuff is. So, for example, for associativity of addition, say, if I want to know that adding the congruence class of A to B first, and then to C, doesn't matter on the order in which I group this, here's what I do. I do my addition, it gives me A plus B, and then I have to add in the congruence class of C. I can combine these two, remembering to use my brackets accordingly. Now I get to rely on the associativity of addition in the integers. So I know that for integers, that expression is the same thing as A plus B plus C, and I can expand this back out. And so you're really using nothing more than the commutative ring structure of Z to prove that same thing for Zn. So next time in the next video I'm going to go into more detail about zero divisors, things which multiply to give you 0, and also about when things are invertible and they have a multiplication.